S a closed surface. And then we know that there's a fundamental group gamma equal pi 1s. And so I'm interested in, as all the other speakers here, somehow interested in representations into G, a simple Lie group. Non-compact type. And I will, in this talk in particular, not be interested in rank 1 Lie groups. I will be interested in higher rank Lie groups. Now, once we have such a Lie group, we can form the symmetric space. This is G mod K. And K is a maximal compact subgroup. This is a very nice space. It is has a geometry. It's a cut-zero space. So it has non-positive curvature. Geodesics between any 2 points are unique and depend smoothly on the point, and so on and so forth. So we can try to use the geometry of the space to study representations of gamma into G. Now let me ask you, put up a few questions. Basically, none of them I can answer properly. So let us assume we have a discrete phaseful representation. So then we obtain a flat bundle as follows. So we take, I think of it now as being gamma being, for the sake of simplicity, being now a subgroup of PSL2R, because I know that this surface subgroup is, of course, can be embedded into PSL2R as a lattice. So I can obtain a flat bundle. So a quotient, I like the quotient from the left by gamma. So gamma acts on H2 as the fundamental group of the closed hyperbolic surface, and it acts on its X-twiddle via the representation, simply because G is the isometric group of this X-twiddle. And now this is a flat bundle over S. Fiber is this symmetric space X-twiddle. And then can we say something about it? I don't know anything about it. Something about the geometry. We saw already in some talks yesterday that in some instances you can say something intelligent, but this only so far seems to work for special groups G. Now let me look at the space of representations into this Lie group. So this is a space of representations of gamma to G, and we can form the character variety by quotienting out representation by the action of G by conjugation, thinking about if you look for the geometry of your flat bundle, it doesn't change if you change the representation by the conjugation. That's a natural equivalence relation. And now we can look at, we can look at this space and try to find, in particular, try to study components. And special points. Now let me just try to explain what I mean by a special point. G is a very nice group. You should think of it as being essentially a matrix group. Real semi-simple, thank you. Real simple, not semi-simple. I'm never looking at semi-simple, I'm looking at simple. Thank you very much. G is a very nice group. It's essentially a matrix group. So this means that G has many points that are defined over a number of fields. And now if we think about, so for me now the rank, I want to restrict to the rank of, the case that the real rank of G is bigger or equal than 2, then we know that number fields or suitable number fields are associated to lattices in G. So here's a Margulies' theorem. He proved that if gamma lambda in G is a lattice, then lambda is arithmetic. So what does it mean, arithmetic? So arithmetic means that it's defined as a group of the form matrix group. I'm slightly loose here because it will not be important for the rest of my talk, but a matrix group whose entries are elements or integers in a number field. So now you can see that this is not hard to see that this group G is populated by special elements, namely elements that are defined over these number fields. But of course, a lattice, what is a lattice? All elements are defined over the same number field. So the elements in the ring of integers over the same number field. Now you can ask yourself the following question. If I have a surface, then I can construct representations as follows of gamma. So now we know that gamma is generated by, say, A1, B1 standard generating set, AG, BG, and of course, like always, the genus of my surface is supposed to be bigger or equal than 2. I mean, people who study surfaces never talk about the sphere. That will not be interesting. So we know that this group is generated by 2D elements with one relation. What is a relation? I mean, we all know this. This is A1, so the commutator of A1, B1 multiplied with the commutator of AG, BG is equal to 1. So now, and of course, what is character over right here, you just take each of these elements, right? You just map it to some element in G, and then you have one relation, which is one equation. And so in other words, you get, very easily construct representations that way. And now you can just do the following, right? You take the elements AI, BI, and you move it to points that are defined over the same number field. And then comes a small problem, that is this relation. And so it's not entirely clear, although this is a nice equation, whether you can close it up. But of course, morally, you should think of that, there are plenty of representations that are defined over basically every number field that comes into play here. And the question is, how do we find the special points? So how do we find special points? So this question seems quite natural to me, but it doesn't seem to be have been studied to a large extent up to now. So for anyone who is young and energetic, here's a good question, I think, to pursue. Now let me recall that there's a particularized component. This is for the Hitchian component in the case that we look at all elements. So if you put the generators to elements in G that are defined with entries, so you now we represent your G as a group of matrices whose entries are defined elements in this number field, then of course multiples will also be defined in this number field. So all elements are defined over the same number field. Algebraic number field. It's a finite extension of Q. And the number field should be given. I mean, if you, so the point is here, of course, we have here finite generator, so we can always abstractly define the smallest ring in the general. I mean, so you have finitely many entries in the matrices, so you have finitely many elements. So then you abstractly define the smallest ring that contains these elements, but this will not be an algebraic number field in general. So I mean, you want an algebraic number field, a finite extension of Q. And so that's kind of, so in a moment I will come back to this, why this is interesting. But let me point out that you have a Hitchin component in the case P is equal to PSL and R, and here N is bigger or equal than 3. We have seen this before, but let me remind you what the Hitchin component is. The Hitchin component is just given as follows. There exists a unique, irreducible representation of PSL to R into PSL and R. And now what you of course do is you take, you take your group gamma and you represent it as a subgroup of PSL to R, and then you move it into PSL NR via this representation. So this defines an embedding of Teichmüller space, which is a space of all discrete phaseful representations of gamma into PSL to R up to conjugation into the character, or let me take maybe write the character variety. And so the component that contains this representation is called the Hitchin component. The Hitchin component. It's a component containing these. Now we have seen already properties from the Hitchin components. Let me remark that you can try to study, as we have seen before, Hitchin components using analysis, namely Corlett or any other component as well. Corlett showed that for all representation rho, there exists a unique equivariant harmonic map from H2. Now this requires that I represent my group gamma as a lattice in PSL to R. Then I can talk about this equivariant harmonic map into X twiddle, the symmetric space. And so this gives you a geometric representation of this, or geometric representation of the representation. And so for n, we saw already this as well, but I repeat it. For n equals 3, there exists a unique conformal structure or unique point in Teichmüller space such that this map is conformal. And here the great thing about a conformal map, it's a minimal surface. So this means that the intrinsic metric, if it exists, so this conformal map might a priori be branched, but it's known that in this case, it's an unbranched, so it's an immersion. Once you have a conformal immersion, you get a minimal surface. So in other words, you can pull back the metric on the symmetric space to your surface. And this metric, the pullback metric, has non-positive curvature. This is a feature of minimal or conformal harmonic maps on minimal surfaces, that the curvature of the minimal surface is not larger than the curvature of the ambient manifold. Since the curvature of the ambient manifold is non-positive, the minimal surface has non-positive curvature. So here a very beautiful picture evolves. Then you have a space of metrics on your surface that defines or that characterizes the points here in the Hitching component, in the case PSL3R. So basically you get the Hitching component as a space of non-positively curved metrics on your original surface, where you would take the unique representative, which is minimal, and then this minimal representative defines this unique metric, which in turn characterizes the representation. So here comes your geometric structure after all, but it's a geometric structure on the surface. Now, of course, something like this should hold true in higher dimension, but it's open in higher dimension. Let me come back to more general representations and special points. So I have nothing to say towards this beautiful set of questions here, but let me describe first of all what more generally is a geometric feature of such a representation in the Hitching component, namely it's what's called an Anosov representation. And let me describe what this is. First of all, we have the Fuistenbos boundary. Of the symmetric space or of the group, rather the group, this is equal to G mod P, and P is a maximal parabolic subgroup. Now, in the case that we are, that the Lie group is here PSLNR, which is particular explicit, this is just P example, P equal PSLNR, and this is just a space of flags. So what is a flag? So this is a group of linear transformations of Rn, which have determinant 1. And so now we can take Rn, so n minus 1. And what is these AIs are supposed to be linear subspaces of rank I, and they're supposed to be nested in each other. And if you look at such a flag, this is definitely a space on which the group PSLNR acts. And this is exactly the space of, or this can be where sort of the stabilizer of such a flag is a maximal parabolic, and hence the space can be identified with G mod P. So this is just to give you something that is very explicit. So now what is a maximal flat? In the symmetric space X twiddle, this is equal to the maximal rank totally geodesic Euclidean. Euclidean means here with a flat Euclidean metric, Euclidean subspace of X twiddle. So it's isometric to K, where K is a rank of D. And the way we describe it is algebraically. So what is the structure of such a flat? Let me remind this. We can decompose the Lie algebra G of G into P plus K, where K is the algebra of the maximal compact subgroup. That's always a Cartan decomposition. And P is orthogonal for the killing form on the Lie algebra G. And now we take A in P, a maximal abelian. Abelian meaning so the Lie brackets between elements vanish, subalgebra of P. And so the subalgebra defines a maximal flat as follows. So P can be identified with the tangent space of the symmetric space at one point. And now we take the subspace, which is a linear subspace of the, can be identified with a linear subspace of the tangent space. And we just take the exponential map, we exponentiate this A, and then we obtain a maximal flat. And now, so we need the root space decomposition. So this flat is stabilized. This A is stabilized by the Y group, which acts. So this is the stabilizer of A in the group K, in the compact group K. So this acts as a finite reflection group on this linear subspace A. So look at it, view it as a linear subspace of the Lie algebra. And now a fundamental domain A plus for this action. This is a little bit a simplified description, which is suitable for our use. For this action is a Weil chamber. Now, so the nice thing about this description here is, about the Weil chamber, is that we have a Cartan decomposition in the group. This is what gets you going in any theory of anosov representations. So you get a Cartan decomposition. Which is equal to G equal K exp A plus K. So you can write down each element in G as a product of an element in K, an element in the exponential of A plus, and another element in K, so from the left and the right. And so mu of G for G and G is a component such that G is equal to, G is equal to K1 exp mu of G K2 in some way. So this decomposition is not unique, but what's the point is here that this mu of G is unique. This is an element now in A plus is unique, uniquely determined by G. So in this map, mu is called the Cartan projection. Mu goes from G to A plus. It's a Cartan projection. And now why this is a good thing to have is because it describes different qualities of elements in G. So a point G or G in G is regular. The definition if and only if mu of G is contained in the interior of A plus. So this A plus is the fundamental domain for the action of the Weil group. It has boundaries. So for example, the picture could look like this, which is a picture for SO2N. get this picture. So a Weil chamber, or this fundamental domain A plus, is one of these sectors here. So it's a cone or a simplex if you want. And so it makes sense to ask whether you are in the interior or in the boundary. So, and the fact is that geodesics in X twiddle are called regular if their tangent, their velocity is contained in the interior of A plus, so it's regular. And this means that a geodesic is a projection of a one-parameter subgroup in the group G. So it makes sense. So now we have this Cartan projection. It makes sense to ask about that this one-parameter subgroup is defined by an element whose Cartan projection is contained in the interior of A plus, so it's regular. And these are precisely the geodesics. Gamma is contained in a unique maximal flat. And these are the ones where you have a control, and over the other elements it's very hard to get any control whatsoever. So the idea is now, to define a loss of representation. It's called a loss of. If somehow all the corresponding images of geodesics in the surface group, first of all, we require that the surface group is undistorted, so it means it's quasi-isometrically embedded. So Maan talked about this concept yesterday. So that's one requirement, which is actually a consequence of what I'm writing down, but you should think of it. This is one requirement. Then we can talk about images of geodesics in the group. This will be quasi-geodesics in this Lie group G, or in the project to quasi-geodesics in the symmetric space. And then we can ask that this quasi-geodesic in the symmetric space somehow fellow travels a geodesic, which is regular. For the other geodesics, it turns out this doesn't make much sense to talk about fellow traveling a non-regular geodesic. But if you have one that is regular, although it lies in the flat, it makes some sense to talk about it. And so this is captured in the following definition. Representation is the north of if there exists an equivalent embedding of the boundary of gamma. So gamma is a hyperbolic group, so it has a Gromov boundary, which is just the boundary of the hyperbolic plane, which is just equal to S1 in this case, into G mod P, the Fuistenbos boundary. And now this Fuistenbos boundary is exactly the space of all asymptotics of sectors, or these Weil chambers. In the symmetric space, you should think of an exponential of A plus as being an embedded cone in the symmetric space, which somehow goes to infinity. And two such things are equivalent if their distance is uniformly bounded. And now you should think of this space G mod P as a space of all asymptotic equivalence classes of these Weil chambers. So then we want an embedding into G mod P. In other words, you should think of that each of these points goes to an asymptotic Weil chamber if you want, or an asymptotic flat. And we want that such that all x not equal to y in S1, so the image f of x and f of y are antipodal, which means that there exists and regular, which means that there exists a geodesic. By definition, this means that there exists a geodesic in the gamma in the symmetric space X twiddle, which connects f of x to f of y, and this is regular. It's a regular geodesic. Now you can see already in this picture that not any 2 points can be antipodal, and not any 2 of these chambers can be antipodal. Take this picture. This is a picture where we decompose an R2, a flat R2, into sectors, right? So each of these sectors here corresponds to 1 point on this G mod P. If we take adjacent sectors, there is no geodesic connecting them, because geodesics in the R2 are just flat geodesics, and not any 2 points on the boundary of R2, the visual boundary of R2 can be connected by a geodesic. So these 2 sectors, they are antipodal because there's an obvious geodesic that just crosses through, but these adjacent sectors are not antipodal. So you have to be very careful. But we want that these these points here are antipodal in this sense. And so this defines a class of representations. And so here, Hitchin representations are Anosov. So the class of representations, the Anosov representations contains a class of Hitchin representations. These are the only representations I have any understanding whatsoever about. So there is, of course, these are the best studied representations because in some sense they are the easiest one. And so there is extensive work on these representations due to François Guéry, Olivier Guichard, Fanny Kassel, Anna Wienhardt, and sort of independently and complementary by Misha Kapovich, Bernard Leeb, and Jean Porti. So these 2 groups of people, so the theory was initiated by Labourie, as far as I know, and was then further extended. So Guichard and Wienhardt extended the theory in a more general framework, or give us, in some sense, a reinterpretation of the theory. Now the work of Guéry, Guichard, Kassel and Wienhardt, and Kapovich, Leeb and Porti puts it on a completely new sort of footing. In some sense, it's more now a theory that is much more general and much better understood and is more geometric. So these guys here produced something like 300 pages, and these guys produced, I don't know how many pages, but they're definitely more than 100. But so there's lots of pages that you can read if you want to study Anosov representations. So this is, that's now a kind of an industry somehow to get a better grasp on these representations. All right. So now I don't want to talk about further about these works, so I just want to give you these references and introduce them and also representations. So here's a question which I have absolutely no idea how to answer this. Can you find special points arbitrarily near Teichmüller space? So now we understood how to describe or give some flavor of these representations. Now let me come back to the original definition of the Hitchin component. Here you have Teichmüller space. The Teichmüller space contains special points because there are arithmetic surfaces that define special points. But of course, there are lots of non-arithmetic points as well. And now the question is, is there an arbitrary deformation of Teichmüller space or a point arbitrary near Teichmüller space, but not on Teichmüller space, which is a special point. I have no idea, but I mean, I will sort of spend the rest of the time here to give you some idea how to construct special points that definitely do not lie on Teichmüller space. Now, for this, let me introduce a special point, different special point in this Weil chamber. So you can associate to this, this decomposition of A into this fundamental domains for the action of the Weil group. There's an associated root system, since it will not play any role. I don't bother you with introducing it. But I mean, there's a special point, which is sort of the maximal, the sum of all the positive roots, and is a point in the interior of the Weil chamber. All right. Sorry? Yeah, sure, yes. So I mean, in the way I embedded Teichmüller space beforehand, and this is, of course, called the Fuchsian locus, but I wanted to spare you. It gives too many names to too many things, but since you know all these names, I may as well spell it out. So, but in this, in such a Weil chamber, there's a special vector or special point, which is a barycenter, and it's just the sum of the positive roots, whatever that is. But this barycenter direction has a particularly nice geometric description. So in A plus, you have the barycenter. We call it B. And so this is the direction of the maximal volume growth. So that's, let me be a little bit informal here. This is kind of easy to describe what that means, but I mean, in order to write it down precisely, I would have to spend more words than I wanted to. Let me just give you a picture, right? I mean, so you start with a base point, now you just in the symmetric space. And now you just look at the exponential map, and you look at the distance sphere of radius r. So this is the image of under the exponential map of the sphere and the tangent space of radius r, right? Now you go along a geodesic, which has some direction, and you ask yourself, what is the volume growth along the geodesic, meaning that now you take an orthonormal basis which is in the tangent space of the over that point, which is orthogonal to the distinguished vector, which so you take an orthonormal basis of the subspace of the tangent space, which is the orthogonal complement of this distinguished vector in which direction you go, and then you ask yourself what the differential of the exponential map does for the volume. So you take the subspace, and this defines you, I mean, you push it forward with the exponential map, and you ask for the determinant of the exponential map basically at that point where you go to distance r. And this determinant is largest if you are in the barycenter direction. It's strictly smaller if you are in any other direction. It's very different from a rank 1 symmetric space. So this gives you, I mean, a growth condition. And now you should think of this growth condition also if you have a lattice. This barycenter direction will be the direction that attracts most of the points in the lattice, simply because the lattice slides fundamental domain. And if the volume growth in some direction is bigger than the volume growth in other directions, then you will somehow see more points in the lattice in this direction as you move to infinity. This can, of course, be made precise. Now, this is the informal explanation why this barycenter direction is maybe perhaps the most important direction. But now let me give you a slightly more formal way how to, why we like, or the way I like to use this barycenter direction. Now what I like to do is I take lambda in G, co-compact lattice, and I want to construct special points. So this gives you special points if I find a representation of, say, a representation gamma, a row of gamma into lambda, which is phaseful, then I get a special point in special Anosov representation. To what I like to do is, so the goal will be construct an Anosov representation. So all Anosov representations are discrete and phaseful. Anosov representation of gamma into lambda. So it's an Anosov representation of the surface group into G, whose image is contained in this lambda, and this gives us a special point. This defines a special point. So again, I mean, so I have to be careful in which component I land, because Anosov representations strictly include the Hitchin. Say if I start with PSL and I strictly include the Hitchin representations, but I can arrange them so to be Hitchin. So for example, in the Hitchin component. And again, this will be a special point because the lattice is arithmetic. However, I mean, the caveat, as you will see at the end, the caveat will be that these are very far away. Function locus of the Teichmüller space. I have no idea how to construct Anosov representations that are special points that are close to the Teichmüller space. So now for the rest of my time, I will give you some outline how to construct those guys. We start with this lambda, and so this is arbitrary but co-compact. Most lattices tend to be not to be co-compact. I have no idea how to deal with them, but anyway. So now the idea is to use some geometry. So let me point out one first feature. So let us assume gamma in X twiddle is a regular geodesic. Now again, I fix for the rest of the talk, I fix this lambda. It's arbitrary but co-compact. And maybe I want to have it torsion-free for simplicity. This can always be arranged simply because there's Selbach's lemma, which says that every lattice in a Lie group has a subgroup of finite index, which is torsion-free. So in the worst case, I can go to the subgroup of finite index and make it torsion-free. Even for the argument, it doesn't matter, but I like it to be a torsion-free. So let's assume this. So now let us assume that we have this regular geodesic, which closes up to a periodic geodesic. In the quotient manifold, this is now manifold, so I take the quotient of X twiddle over lambda. This is a locally symmetric manifold, which is compact. And if we have this, then the claim, and this is an old result, and it's very easy. Due to Bohrer and Schröder. This is not an isolated guy. It sits in a compact torus of maximal rank. So there exists a compact torus T in totally geodesic flat totally geodesic embedded. Containing gamma. So how should we think about this torus? There's a very simple way to think about it. How do I get a torus? I forgot one statement, maximal rank. Rank is equal to the rank of G. How should I think about such a torus? There's a very simple way to think about it. How do I produce a torus? A torus is nothing else but an RK divided out by a lattice, and the lattice is Z to the power K. So my T is equal to now, if I want to have this guy embedded, this torus embedded into this locally symmetric manifold, the fundamental group of this locally symmetric manifold is lambda. But if I have this totally geodesic embedded torus here, then the fundamental group of the torus is a subgroup of this lambda. So in other words, the way I produce such a torus is lambda intersects stabilizer of the unique maximal flat containing this geodesic gamma. So here I pick the geodesic. Actually, what I'm saying here is a little bit lying because you have to worry about conjugates. But I mean, morally it's correct. So unique maximal flat containing gamma in a lattice. So here we have this beautiful picture that we have a totally geodesic embedded R2 in this, or RK in the symmetric space. You look at the stabilizer, and the stabilizer intersects the lattice of the lattice in G in a lattice. That's very nice. And this way we produce such a torus. So we, in other words, what I'm saying here is as soon as you see a closed geodesic, you see a torus. So this means that this locally symmetric manifold is populated by tori. So there are plenty and plenty and plenty, countably many tori that link around. And so this somehow gives a lot of, on the one hand, it gives a lot of structure to this locally symmetric manifold. On the other hand, it's a little bit fighting against producing surface subgroups, because the surface subgroup is, I mean, we talk about higher rank surfaces. So surface subgroup is something that has negative curvature, so it's a hyperbolic group. So this is not compatible with having all these flats here, right? So now let me give you some information on the organization of these flats. So here's an interesting question, I think. Let's assume, so this is a small side remark, interesting question. So let us assume K is equal to 2. So the rank is equal to 2. Then this torus will be a 2 torus. But we know that there's a moduli space of 2 tori. So there's this is basically a version of the Teichmüller theory. So we can look at the moduli space of 2 tori. And so 2 tori come in different shapes. So this flat 2 tori come in different shapes. They can be sort of long and skinny, but they can also be sort of pretty much round and nice. But so each such, in this case, each such torus defines a point in the moduli space of tori, which is equal to H2 divided out, maybe I want to write it from the left, PSL to Z. So what are these points? So we get countably many points in this modular space of tori. What are these points? How are they distributed? So that's an interesting question. The discouraging thing is, if you want to study this question, you are automatically studying class field theory. So we are talking about an arithmetic lattice, and then it turns out this is class field theory. Let me give you, nevertheless, some counting result, which is not hard. So how do we sort out these tori? So we can sort of basically count them according to the system. So each of these tori has a system. It's the shortest closed geodesic. Now what we can do is, now we take, let's discuss the general case where the rank doesn't have to be 2. We can just try to sort out these tori that we see here by system. So they're the shortest closed geodesic. So the system is definitely grounded from below, because each of these geodesics defines a non-trivial element in the fundamental group, so that so the lengths cannot be arbitrarily short. So we can just count them according to the system. And here's this theorem, which is actually relatively easy to prove. It was proved by myself, but it's an old theorem by Deitmer. Deitmer used a Selbach trace formula to prove this, but it actually can be deduced with standard methods of hyperbolic flows. So you can, the following holds true. So if you count over all t such that the system of t is less or equal than r, and now you take the volume of t. So what you do is you sort for all t's where the system is less or equal than r, and then you don't take the system, but you take the volume of the tori. So the volume might be kind of very complicated. So the volume is at least the system square roughly, but it might be much, 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 much larger. And this is asymptotic to e to the power br. And this b is just the norm of the barycenter. So the barycenter has this barycenter is a sum of the positive root. It has a natural norm coming from the killing form. And this is asymptotic to e to the power br as r goes to infinity. That's something that you can prove. And again, this is actually not particularly hard. So what is much more harder and completely unknown is in hyperbolic. So in the hyperbolic setting, like if you look at the rank, in the rank 1 case, like the ambient symmetric spaces, say the hyperbolic plane, then you would count your conjugacy classes of periodic geodesics. So that means you would count conjugacy classes of elements in the fundamental group sorted out by the length. Now, any count on conjugacy classes of elements in lambda, in such a lattice lambda, if the rank of the ambient Lie group is at least 2, it's absolutely unknown. And it was only recently established that the growth is exponential, but we know nothing about the growth rate. And again, why is this very hard? This is easy. If you plug in the volume, but the volume here, this could become exponential. Related in regard to the system, the volume could be enormously large, exponential in the system. This defies all the counting efforts. And in order to sort this out, you would have to do presumably class field theory as well, unless you find some other tricks. Yes? Yeah, this is the B is the entropy. So the B is equal for so we are here in a locally symmetric setting. So the B would be exactly the volume growth rate So this is 1 for the, 1 over, it's 1 for H2 and so on and so forth. So, I mean, there's this classical theorem of Margulies for Noether flows where this is not what you get, but you divide it over HR, but here it takes a volume and this reproduces the R. So this is exactly Margulies' formula in the case of rank 1 lattices in rank 1 Lie groups. So it's exactly the same, slightly rewritten. All right. So now let me finally give you a way to produce these special points in the character variety. So what you do is you use a method that is due to Kahn and Markovich, and I tell you how you can adopt this. So you look at this barycenter space, barycenter direction P. So why is this good? So you can do the following. So you look at the space, the subspace of the unit tangent bundle of this X twiddle of vectors is the barycenter direction. That means for each of these flats, these sectors, you pick this one precise vector, and you forget all the other ones. So this is actually a homogeneous space. It's not G mod K, it's G mod something like K prime or some compact subgroup which is smaller than K. And now you can do the following. So this is invariant under the geodesic flow. This is somehow straightforward by the construction that is invariant because geodesics are images of under the exponential, so basically one parameter subgroups projected to the symmetric space. And now if you have, if you start in a barycenter direction so that you have a one parameter subgroup in the barycenter direction, you will stay in the barycenter direction for all times. Phi. What does it do? So phi t is a flow which maps a unit tangent vector in X twiddle to gamma v prime of t. So this is a unit tangent of the geodesic direction v at time t. So now, I mean, this is not a manifold because, as you can see, there are these sectors that are in the way to having a manifold. But I mean, it's nice. So it's a homogeneous space. A homogeneous space doesn't have to be a manifold, nevertheless. So it doesn't have to be a manifold unnecessarily. But I mean, once you have a homogeneous space, there exists an invariant measure. Flow invariant. This is somehow a projection of the Haar measure. It doesn't have to be a manifold because it's the torsion points. It's an orbifold. I mean, this is completely harmless. It's not a manifold. There is there are these barycenters that come together at one sort of around the Weyl chambers. It doesn't have to be a manifold. Yeah, Yeah, it's only virtually G-mod K prime. I mean, there's this, I'm slightly lying here because there's a Y group. I mean, the Y group is always in your way. But this is invariant measure, so the projection of Haar measure. So I mean, this, yeah, I shouldn't have written it in this way anyway. So, but it's anyway, it has a projection of a Haar measure, and which is a flow invariant, and so now you can project it. So now if you can project this measure finite. On lambda G mod. Yeah, I shouldn't have written this in the case. So I could pass to a finite. This is a good or before that I could pass to a finite. It doesn't really matter to a finite cover here, but so I take it in a way which is invariant under the flow. Now, so what I like to do is now I produce, so now a couple of steps. So the first step is step 1, produce periodic orbits. So this is relatively easy. This you use recurrence. You now have a flow in a compact space. Use recurrence of the flow. This is, I don't have time to explain to you exactly what you need. You need proximality of a certain proximality statement about elements in this Lie group G, which I'm not going to explain. So the idea is roughly the following. If you have an orbit that comes very close to itself, then you close it up. And what you want to show is closing up is always possible. This is kind of a very elementary operation. What you want to show is that you have a periodic orbit nearby where you have to do something. In the rank 1 case, it's very easy, but here in the higher rank case, you have to be slightly careful. So that's, but this is not, it's not all that hard. Now, what you want to do is you want to soup it up. So you produce this way periodic orbits that are controlled, so you can control the length. What you want to do it, you want to soup it up to produce almost hyperbolic pairs of pans. So step 2, construct almost hyperbolic. Hyperbolic meaning they have some pairs of pans that are embedded in this, or maybe immersed in this quotient manifold. In the now we look at the quotient manifold G mod lambda. It is actually manifold that are immersed there, and with intrinsic geometry which has almost a curvature very near to -1, so almost hyperbolic pairs of pans. So how do you do this? What you realize is there are, of course, directions where the curvature is negative. So you have planes in G mod lambda of curvature -1 that actually are contained in a totally geodesic immersed hyperbolic plane. So once you pick such an immersed hyperbolic plane, you pick a point and you look at a tripod where all the angles are equal. So these are tangent vectors in this hyperbolic plane. All the angles are 120 degrees. Now what you do is you start moving with your geodesic. And you can arrange that these directions are all in the barycenter direction. So you move with your geodesic. You move along with these geodesics. And you try to connect this picture to another one where you have another of these tripods. Let me draw it here. The idea is now due to sort of dynamics of this flow down here, you will find times where all these guys say are close by. They don't close up. They come together but in opposite direction. So they're not really the same vectors, but they come together and almost in opposite direction. So here's a little gap here. There's a little gap here. And there's a little gap here. Right. And then you use what I said before. If things come very close and they're in a good direction, the barycenter direction. This is barycenter, this is the negative of barycenter. It's a little bit a matter of taste how you describe it. So you go backwards. And so they come very close, and you can close it up. I mean, just connecting them somehow. And in this closed up picture, you find a closed geodesic, which is very near. So you define a pair of pairs. So this is not, it doesn't come here, the angle is 120 degrees, but you are in a totally geodesic hyperbolic plane. So this means it really looks like if you had to produce the pans in a hyperbolic surface. So this avoids this angle here as it would do in the hyperbolic plane. You think of it as the relevant sort of problem is very far away from this 120 degree angle, and this produces you a pair of pans. This looks here exactly the same. Here's one. And there's another one. So these are almost hyperbolic. So we can put a metric on them so that they're almost very close to a hyperbolic metric. And again, the only problem is at these connectors where you have to do something in order to get these boundary geodesics, but they will be very close to hyperbolic. And now you want to glue them up. Define a surface. And so these pairs of pans will be, of course, incompressible. That means the map from the fundamental group will be injective simply because they're almost totally geodesically immersed. But now you want to glue them up, and you realize that you have a problem because due to the flats. No, these tripods are arbitrary. This is the dynamics of the flow that matches them up. They're coming very close and they're almost parallel, yes. So the dynamics of the flow arranges, so will assure that eventually this is going to happen. So for most of them. So somehow the dynamic is that for this is exponential mixing, which I don't want to explain what that means, but this is guarantees you that they come very close to each other. And now you have to glue them. So glue these pans. Glue pans. With the same boundary, or with the sharing a boundary geodesic. To an incompressible surface. And now you have a problem because you don't know how to control things. That's very hard. But here's the trick. So you cannot do this. You don't have enough control in a higher rank symmetric space. But here's a trick. Remember that each of these geodesics lies on a torus. So let us now assume that we are in the, almost done. Let us assume that we are in a rank, 5 more minutes, in the rank 2 case, right? That's a simple example. What can we do if we want to sort of get control? We come here, so here's a geodesic lying on a torus. Here's my torus, right? Let me draw this picture. The flat torus. But now I want to have some sort of control on the global properties of the elements in the fundamental group that are described by geodesics on the glued up picture. And I can't because the flat torus is in my way. But what I can do is, so here comes a pair of planes. This is sort of transverse to the flat torus because this is in a hyperbolic direction. The flat torus is orthogonal to it. And another pan is also, going down the other way. It's orthogonal to the flat torus and goes in the other way. But I'm not able to get enough control. But what I can do is, instead of gluing this piece of the pans, this pair of pans hyperbolic, Z1, I go around the torus 10 million times. This amounts to a partial conjugation. So let us assume that I have already here a surface with one where the only boundary component is this one, I have another surface where the only boundary component is that one, and I want to make sure that what I glue up is incompressible. What I do is I take a partial conjugation by an element in the fundamental group of the torus, which goes around the torus here of colored chalk, not along the boundary component, but goes around the torus this way, which amounts to gluing this torus maybe 10 million times. So I start with this pair of pans, then I glue the torus in 10 million times, and then I keep on going the other way. What this assures me is that this amounts to a partial conjugation of this one surface group with this element here, and then I glue it to the other surface group. What this allows me is to separate these two groups and get incompressibility. So I use these tori, closed tori, in this manifold to glue large flat annuli to my partial surface to the pans and assure incompressibility. Now let me just finish with remarking that this, of course, produces a surface which is a representation, special point, which is very far away from the Hitch, from the Teichmüller's representation, because these flat torus will be enormous. So at the end of the day, depending on my situation, I might have to glue such enormously many of flat tori in that this representation goes very close to the boundary of, say, the Hitchin component I started off with. But that's the price I have to pay. But as you can see, if you ask me to produce a special point close to the boundary of the Hitchin component, we understand a little bit what happens if we degenerate the Hitchin component. So more and more flats kick in, then I can produce these special points very near the boundary. But for strange reason, I'm not able at the moment to produce you special points that are very near Teichmüller space, except the point that I have on Teichmüller space. Thank you very much. Because I'm in the lattice, I get an incompressible, I get a representation whose image is in the subgroup of the lattice.
Excuse me.
It's a good question. I can take any other regular direction and play the same game. I have to be more careful. The barycenter direction gives you more room. And the point is that if you look at the geometric picture, you have to take sort of orthogonal, totally geodesic hyperbolic planes. You get more geometric control if you use a barycenter. The barycenter is the best direction. But if you make a little effort, then you can of course do all other regular directions. But you have to, again, I mean, you have to be more careful.
So how do you see that this gives you a surface subgroup that's in the image of some Hitchian representation?
That's by construction somehow. If the pans, so I'm starting, so assuming that I'm in PSL NR, right? If I could glue the pans are essentially hyperbolic. If I could glue the pans in such a way that it matched up here, so then I'm fine anyway, right? Because then I'm essentially in Teichmüller space.
Excuse me, how are you choosing these tripods between, I mean, to construct the pans?
Sorry?
How are you choosing these tripods, the one that you used in the picture?
I have to use all tripods.
Okay.
Point is, I mean, this is, so this, basically you take all the all the planes that lie in totally geodesic embedded hyperbolic planes. You take all the tripods in all the planes. You do this construction with everything. That gives you, I mean, basically gives you an enormous number of closed orbits. I mean, there's of course double counting, because if you start with a very nearby tripod, you get the same closed orbit. It's very hard to control. But the point is, you start with all the tripods and you use basically dynamics to produce, I mean, all these pairs of pans. So you get an enormous number of pairs of pans. And of course, the length of the boundary length of these pairs of pans is enormous. There's very large, the length of the boundary curves is very large. And sort of the only question is how to glue these guys. I mean, producing these pairs of pans, you get zillions of pairs of pans. It's very hard to distinguish. I mean, you start with a nearby tripod. It's very hard to say whether you get the same pairs of pans or not. But you start with all of them. Just glue them. You produce an enormous amount, but you don't care. I mean, as long as you have these pairs of pans, then this is, so you need them in basically going in all directions. That's fine because you start in all directions. And then you just have to glue them, but the gluing is the hard part. You want to glue them not to get a surface, but you want to glue them to get an incompressible surface. That means such that the map induced by the injection is an injection of fundamental groups. That's a hard part. I mean, so otherwise, I wouldn't have to work at all if I wanted to have some representation. I mean, here comes the question with the Hitching component, right? I want an incompressible representation. I want it to be a Nosov. So I have to do all the work to get this done. And then so at the end of the day, if I'm in the nice Lie group, I want it in the Hitching component, which at the end of the day is then not hard because I get all the Nosov and this stuff I get beforehand. So that's the way you do. You cannot do this. I mean, so the first urge would be to try to do something similar, but you need an exponential control on the thin part of the pair of pans. And since you have these flats, I don't know how to get this. I mean, so basically the gap has to be exponentially small. But you have the flats. So in other words, if you close up these loops to make a closed geodesic, then you lose some, you get control, but you lose control due to the flat. You don't get exponential control. And this is not, I mean, I don't see how to make this going. I mean, how to make this work. But here's this, I mean, this is a trick that sort of tells you, okay, I mean, actually the higher rank helps you. Because now with this sort of looking at the TOR, you really separate the groups. So some sort of ping pong construction, if you want, using the fact that the elements that describe these closed loops are definitively proximal. So they're nice elements in the Lie group. So they have this sort of now more self-dynamics Yeah, so basically I shift, but the point is that, of course, I move then along this blue thing, right? And I move them away from the actual sort of, so in other words, the surface then looks like this, right? Here you have the pair of pans, it's hyperbolic. And you have this enormously long, it looks like rafting, right? Enormously long flat cylinder. And then you glue the other one on. But this flat cylinder somehow moves the pieces of the group, moves it away. It's some sort of combination thing. Right. Which result?
So, this Vargas-Schroeder result is true for also non-co-compact lattice. If I take a non-co-compact lattice.
Sorry, which result?
There, this.
Good question. Vargas-Schroeder. I'm not sure because you could go off to infinity. I'm not sure. So the idea is that, I mean, the proof is very simple. The proof is very naive, right? I mean, you have once you have a closed geodesic, let's look at the rank 2 case, but it works in every rank. Once you have a closed geodesic, you get a flat cylinder, right? I mean, because you have this flat, and so you get an immersed flat cylinder, and you slide your geodesic along the cylinder, so that's fine. If the cylinder comes back to itself, which it has to do, if you have a co-compact lattice, then the cylinder has to somehow come back near. So there's an accumulation point if you want, right? Then if you have an accumulation point, since you have positive injectivity radius, you have two closed, I mean, you have one closed orbit, you have another one that sort of goes along the cylinder and comes back very close. They have to be exactly coming from the same element in the group and not by any conjugate or anything because you have positive injectivity radius. That proves it. In other words, you have this in the universal covering. So you have this, you take one of these closed orbit, you move it to a periodic geodesic in the universal covering. There's a tubular neighborhood which is precisely invariant under the group. But now this other, so now you have another orbit which comes comes very near. You have this other guy which sits in this tubular neighborhood, who sits in this tubular neighborhood. It has to come from the same group element, so it has to close up. But in the finite volume case, maybe it's true, probably it's true, but I don't know. I mean, I don't quite remember. But the argument again is very simple.